Is that what it
Okay, effective rate. Effective rate has a formula, and you can plug into the formula to find out what the effective rate is. That's not something you can do on the solver. It does not do effective rate, so you have to use the formula. But suppose you deposited $1 at 6% interest compounded semi-annually. In that case, the interest rate would be the annual rate divided by the number of compoundings, which would be 6% or 0.06 divided by 2, and that would give us 3%. So 3% per period, and then N is 2 periods. And at the end of the year, the compound amount would be, if you substitute into the compound interest formula, 1.06090, and that shows that $1 will increase to $1 and basically 6 cents, which is an annual increase if you keep all the decimals of 6.09%. The actual increase, 6.09% in the money, is somewhat higher than the 6% stated interest rate, and that's because they compounded more than once during the year. So you were actually getting interest on your second compounding period based on not only what you put in to start with, but the interest for the first compounding period. So to differentiate between the two numbers, the 6.09% and the 6%, 6% is called the nominal rate or the stated rate. It's always the APR, the annual interest rate. And 6.09% is called the effective rate. So to avoid confusion between stated rates and effective rates, we will use R for the stated rate and R sub E for the effective rate. And the effective rate, a great many times, is higher than what the stated rate or the nominal rate is. So here we've got the formula. And we're going to look for an effective rate for an account that pays 2.7% compounded monthly. Okay, so that's 2.7% annual rate, but they're going to compound it 12 times in 1 year. So your effective rate for your term 5 problem is given by R sub E, which is plugging into the formula 1 plus R over M raised to the M power minus 1. And since your nominal rate is 2.7%, that's 0.027. And the number of times you're compounding a year is 12 because you compound monthly. And then you raise that to the 12th power, subtract 1, and if you do the arithmetic, and again, it's important that you do the arithmetic carefully, then your effective rate is 2.73%. So it's a little bit higher than the nominal rate. Now, you don't have to memorize any of these formulas. These formulas will be given to you on the test. I do not expect you to memorize these. In fact, I don't think any bankers actually memorize these or anybody else in finance. They always have a program that calculates these things for them. That's the beauty of Excel. Did I go too fast? Okay. The next problem we have in section 5.1 is to determine present value. Now for this you actually can use the solver, but the formula for present value isn't difficult. Present value is when you take the formula for compound interest, which is A equals A, the future value, equals P, the present value, or the principal, times the sum of 1 plus the interest rate for the power of N, where N is the number of years. And the present value, if you solve that for P, you come out with the formula that the present value is equal to the future value times the sum of 1 and the interest rate But the power is going to be to the negative n power because you're actually dividing by 1 plus I raised to the n power. Now there's two places this is very important to you. Number one is in this chapter for finance. I want you to remember that you can have this formula to actually solve your present value. The other thing is I want you to remember when I get you to calculus, because everybody in here should be taking calculus next semester. When I get you in calculus, remember that you can take the denominator of a rational expression that has a power on it and move it into the numerator and make the power negative. That's going to be an important algebra concept. So you need to remember that too. Your algebra skills are going to be important in business calculus. So this is an illustration of the kind of skills you need to have. So here's an example for present value. We're going to find the present value in 7 years if money deposited at 4.25 interest rate is compounded quarterly. So what we have to figure out here is what all of our variables are. So if it's compounded quarterly, that's 4 times a year. And if you are going to invest this money for 7 years, then that's 28 compounding times. The rate of 4.25% per year has to be divided by 4 because you're compounding quarterly. So you apply the formula. A is the future value, which is $10,000. Your actual interest rate is 0.0425 divided by 4, which is 0.010625. And then your number of compoundings, as we said, was 28. So plug all that into the formula, and if you, basically what this concludes is that if you deposited $7,438.39 today into an account that was paying an interest rate of 4.25% compounded quarterly, you would have a total of $10,000 in 7 years. So your investment of less than $7,500 at actually a relatively low interest rate turns into $10,000 in 7 years. Does anybody have any questions so far? Now when I give you the next test, all of the next test is going to be word problems. It has to be, because there's no point in having finance formulas if you don't figure out how to apply them. You know, just plugging numbers into a formula is not going to help. It's all going to be word problems. What I'm going to have you do is I'm going to have you identify every variable separately from the formula. And then you'll have the formula. You'll have a sheet of formulas. Then I want you to show me what you plugged into the formula and then do the arithmetic. That way, if you messed up on the very first step, at least I know where you messed up. You misidentified one of the variables. If you messed up the arithmetic, that doesn't mean your whole problem is going to be wrong. It means that I can give you credit for at least knowing what the variables were. Okay? Now you could also have done that problem on the graphing calculator. And what they've done here is what I'm going to demonstrate for you on the calculator itself. And I'm going to go back to problem to do it. Let's get the calculator. And there's more than one way to solve it on the calculator too. You can use the graph, or you can also use the solver. So we're going to go to the y equals menu, and what we're going to enter into the y equals menu is going to be the formula with the variables plugged in, only what we're going to do is we're going to leave out probably part of that. So we're going to put in, find the present value of $10,000, so that's A. And we're going to divide A by 1 plus the interest rate. And the interest rate isn't going to change, so that's going to be, we could just put in the 0.0425 divided by 4, but I'll go ahead and take the actual divided out number, so that's going to be 0.010625. And even though we know n, we're going to let x be the number of years. So we're going to raise that to the power of 4 times a year for X years. So we're going to raise it to the power of 4x. So we can watch what happens over the 7-year period. And then what we want to do is see what happens. Actually, I think I just did that wrong, because that's going to find the present value. Oh, mine will actually work though. So let's go to Window and go 0 to 10, and then do Zoom, and I'm going to use Zoom Fit. I'm not going to have to hunt for one. I'm going to let the calculator set the Y's up for me. And if I enter this correctly, I can ask it, show me what the value is in 7 years. That didn't work, so I'm going to enter my formula. Let me look at my formula. Okay, I can't see what I did, which happens sometimes because I think what I did was right. So let's go look at the technology note in the book. And I know if you're like most of the people that I went to school with, you don't really read the math book, but occasionally it does have some good advice. So we're going to go to Chapter 5, Mathematics of Finance, 5.1. This is on 220. If not, this at least will get me in the neighborhood. A little bit further. Next page. Oh, I was looking at the wrong graph. That's why mine isn't matching up with what we're doing. So that's why my answer didn't come out. Let me move that slide. Let's look at the next problem. I think I may have messed up my PowerPoint. Yeah, that one actually goes with an example that I didn't do, so let me pull that slide out. Y'all don't need to worry about it. That one doesn't go with either one of the problems that I kept. I didn't do example 10 because it was done in the book. Okay, let's go on and do the next example. Well, we will go back and do this. Let's look at how we can use the solver. So your solver, remember, is on alpha enter. Well, I'm sorry, not alpha enter. Second, x to the negative 1. We go to the TDM solver. And remember here, n is how many times they're going to compound, so that's going to be 28. The interest rate is going to be what they actually state as the interest rate, so that's going to be 0.0425. We're not interested in making payments. We know the future value, and we enter it as a negative, so the future value is 10,000. And we want to put a 0 in for the present value because we're going to be able to solve for that. And then the number of compoundings per year, the number of compounding periods per year, and the payments of the interest per year is going to be the same. It's going to be 4 times a year because it's quarterly. So then we're going to go back up here to the present value and see if we get the same thing. And in order to get it to calculate that, you click alpha, and I did not do something right. It's because I put in my future value as negative. I think I shouldn't have done that. Thing is not working. Let me make a short recording later of how to do this problem on the solver because something's not working right, and it's probably my memory for what goes into each one of those variables.
I think it was just your percentage.
Is it a percentage?
Well, it was for your value of I.
Let's try.
You put in the 0.04 instead of just 4.25.
You may be right. Let's try 0 there, and then alpha, enter. No, still not it.
Oh, now your N still got to be 28.
Oh, there we go. Thank you. Thank you. Now, in order for you to remember and for me to remember, I like to write things down. So on your solver, I'm going to write it down here, and then I'm going to let y'all look at what I wrote down. We have N, we have I, and it did say percent, so that was my bad. We have a present value, we have a future value, And then P per Y and C per Y have to be equal. And you can leave your payments for now, it needs to stay at the end. So let me get this up here, and we're going to write down what all these stand for, so that you'll have something to help you with remembering how to do these. So this is the TVN solver. N is going to be the number of times compounded. And basically, N is going to have to be the number of years times the number of compoundings per year. I is going to be your interest rate as a percent, because it says percent. PV is your present value. FV is your future value. And PY and CY are both going to be the number of times compounded per year. And then the way the solver works because this will help you check your arithmetic and maybe keep you from making any arithmetic mistakes. The way that this works is you enter everything you know, zero for what you don't know, and then cursor on what you want to solve for. And then alpha and the enter key. And those steps are essentially the same on regardless if it's TI-83, TI-84, TI-83, C plus, or whatever. Okay? So just to play around for a little bit here before we actually go on and finish, let's say the problem had instead given us the interest rate, the number of times per year compounded, but instead of asking for the present value, maybe they gave us a present value of, let's say, $10,000. And what we wanted to know was the future value. Then we put the zero in for future value, put the cursor on that zero, alpha enter to solve, and it says the future value is $13,443.77 without having to do any arithmetic. Okay? If you need a payment, it would find what payments you would need to make into your account in order to have a given future value. So if you wanted to make periodic payments, and what you wanted was this future value of $13,443.76, you would put the present value down as zero, because what you're going to do is you're going to make payments at certain periods. So this would be making a quarterly payment. You'd make a payment at the end of each quarter. And if I want to know how much that payment's going to be, I put my cursor on that zero and alpha solve. And it says if I deposited $414.78 at the end of every quarter for 7 years at that interest rate, then I would still have that same future value. Now, the thing that you need to remember is you're going to need to enter that future value as a negative because you don't have it yet. Okay, you're working on it. And I believe it'll even solve for the interest rate for you. If I remember doing these problems before. So if you put in those payments, and let's say you would like to have let's be conservative, only $10,000 at the end of 7 years. So same payments, but we only want to have $10,000. What interest rate would we have to have? And I think it'll solve and tell you. And it does. It says your interest rate would have to be 4.532%. So the solver will find any one of your variables as long as you know at least the number of compoundings, which means you need to know how long the investment's going to be, and you need to know how many times a year it's going to be compounded. And then as long as you know either the interest rate or the present value or the payment or the future value, as long as you know any three of those, it'll find the fourth one. Or actually, you only need to know any two of those. It'll find the third one, but it won't find all four. Okay? Now, in this case, what if I wanted to know, well, I don't want to make payments. What if I want to know what could I put in the bank today and have $10,000 in the future? Well, I would leave that zero there, put the zero on payment, go back to present value, alpha, enter. And it says if you had that interest rate compounded quarterly for 7 years, you could put in, that doesn't make any sense. Oh, that's because my interest rate's negative. I think that's why. What? Okay, that's better. So it says if I could deposit $7,294.36 today, then in the future I would have $10,000 at that interest rate, compounded quarterly for 7 years. So the solver's handy because it does arithmetic in a flash. So we'll go back to the PowerPoint and try to finish this section up and get on into the next section. Find the time needed for $38,000 deposited at 3.5% compounded semi-annually to be worth at least $7,000. So in this case, the goal is to find N by solving the equation, $38,000 present value, times 1 plus 0.035, the decimal value of the interest rate. It's compounded semi-annually, so divide by 2. And what you want to have is $7,000 or more in the future. And you would need to know what N is. In order to find that, you would have to use logarithms. Okay? The reason you have to use logarithms is because you're going to divide both sides by the 38,000, and that's going to leave you with an expression raised to a power. And in order to find that, the way you solve logarithmic equations is you take the natural logarithm of both sides. Or you solve power equations by taking the natural log of both sides. And that's something probably most of y'all have not done. So the arithmetic method here, since this you definitely have to use a calculator. You take the natural log of 1 plus the interest rate, so 1 plus 0.035 divided by 2. Put all of that inside parentheses. And let's see. You can raise that to the n power. So in our case, that's going to be the x power. And I should have put that at y equals, sorry. And then this actually is just a single number, it's a constant. So you just ask for the natural log of 7,000 divided by 3,800. And I don't think I needed all those parentheses, so let me get rid of the one I started. And in this case, there's 2 or 3 different ways you can do this. You can, again, go to your window, and I'm going to start out at 0 to 10, and go zoom, fit. Okay, way up there is the constant, so I need to increase my window. So I'll go up to about 50. Now I want to see where those two cross. So second, calc, number 5 intersect. So 35.2, we'll call that 35 is the value of n. And actually, since it's a little more than 35, we'll have to round it to 36. So if the calculator gave us the right answer, should match what we get here, and it is 36. You take the natural log of 7,000 divided by 3,800 over the natural log of 1.075, and what you will get is 3521. Okay? So there's 2 different ways to do that. The third way to do it would have been to use your calculator, go onto your table, and probably the best thing to do is to set your table up to where it starts at 1 and increments by 1 and then automatically fills in your table. So then you can go to the table, and what you're looking for is where y1 and y2 have the same value. Okay, so we actually crossed over between here and here. So that says between 35 and 36, so we're going to say that it happened at 36. Okay? So lots of different ways you can do that. The arithmetic's not bad as long as you don't let the natural logs bother you. Now we're going to talk a little bit about continuous compounding. I think we left out one of the problems on here. Let me go back and look. No, that was the one we just did. Okay. Let's talk about continuous compounding. You could compound your payments or your interest on your payments or on your principal once a year. But you would do better if they compounded it twice a year, because then during the second compounding period you would get interest on the interest that you got paid for the first compounding period, right? If you compounded quarterly, you would get even more money, because in compounding period 2 you would get interest on not only what you deposited but the interest from the first quarter, and then in compounding period 3 you would get interest on all the money that was in at the end of compounding period 2 plus the interest on period 2, and so on until you got to the fourth quarter, you're actually going to get interest on all the money that you originally deposited, plus the interest that was paid at the first compounding period, plus the interest paid at the second compounding period, which was even more than the first one, plus the interest that was paid on the third compounding period, which was again even more than the previous period. But if you go to monthly, it compounds again more often, and each time it compounds on a continuously larger amount, so you get even more money. There are, like we said last time, we would assume 360 days in a year, so what if it compounded every day? Wow. You would think it would make a huge difference. If you compounded every hour, now look at the amounts here. Quarterly, we got 3438.78. Monthly, for whatever we deposited at whatever interest rate, if we compounded at that same interest rate that compounded monthly, we only get what? $5 and change more? Not very much. If you compound daily, you get about between $7 and $8 more. If you compound it every hour, you get a whopping 8 cents more. What does that tell you happens as your compounding periods become more and more and more frequent? Eventually, they don't make any difference, do they? If you want to do continuous compounding without having to sit there and go through, okay, quarterly, monthly, daily, hourly, the number E is the natural logarithm of 1. It's a number that shows up a lot in business and economics. It's a number that shows up a lot in science. It is a constant. It is not a variable. Okay? It's a constant, the natural logarithm of 1. And if you want to know what the value of E is, you can ask your calculator. It will happily tell you. Second ln gets you the E because those are inverse functions of each other. And e to the first power. Oh, sorry. Let's try that again. I had something in there already. So E is we usually say it's 2.7183. We don't usually go beyond that, but it actually is an irrational number like pi. Just like pi is actually defined as being the ratio of a circle to its circle's circumference to its diameter. Well, E is the natural logarithm of 1. That's just what it is. And it's useful to us in this formula because if we want to find a present value at an interest rate R being compounded continuously for T years, then the future value can be found using this formula. It's an easy formula to use. So we'll do an example of this one. We're going to find the interest earned on $5,000 deposited at 3.8%, compounded continuously for 9 years. So in this case, our present value is our $5,000. Our interest rate, 3.8%, we convert to a decimal, 0.038. 9 years means our compoundings are going to be 9 because it's compounded continuously for 9 years. So the formula when you plug in is 5,000 times E raised to the 0.038 times 9 equals $7,038.80. And the amount of interest earned is $2,038.80. So as far as entering that in on your calculator, the way you want to enter it in is just simply 5,000 times E, which is second ln, and then the power of E is 0.038 times 9. And you don't have to put either of those in parentheses, you just enter the multiplication because it will do that multiplication inside the parentheses before it turns it into a power. And just hit enter and there's your answer. You can't use the solver on this one either. It doesn't have continuous compounding that I've been able to figure out. And once again, I will give you the formulas. You don't need to memorize them. Questions on that one? So these are all the formulas that we've looked at in this chapter. Now what I will give you is I will give you the formula. It is up to you to remember what all those variables stand for. Okay? I think what we'll do next class period is I'm going to bring some index cards in here and have you write all of those formulas on the index cards. And then I want you to fill out what each one of those variables stands for so that you can not memorize the formula, but memorize what the variables are. Okay? So we'll come back and review that one. So now we should be ready to go to section 5.2 and talk about something called annuities. Now this first slide is a lot about language. Finance has its own language. A sequence of equal payments made at equal periods of time is called an annuity. An annuity, for the most part, is regarded as being a savings account or some kind of an investment. For example, I have an annuity account with Thrivent where I make a specified payment at the end of every month, and they have a set interest rate that they pay me on that. And my annuity at some future point in time will earn interest, and I'm going to use that to pay for a retirement account. So it's basically like a savings account. But the annuity has what's called a maturity date, and the maturity date is going to be, for me, the year that I retire. So that's kind of what an annuity is. If you make your payments at the end of each time period, which is what I do, and if the frequency of the payments is the same as the frequency of the compounding, and in my case it is, they compound, I make monthly payments and they compound monthly, it's called an ordinary annuity. The time between the payments is the payment period. I make my payments the first of every month, so my payment period is 30 days or 1 month. And the time from the beginning of the first payment period to the end of the last payment period is called the term of the annuity. My annuity is a 30-year annuity, and I'm going to make 360 payments into it. The future value of the annuity is the final sum on deposit and is defined as the sum, sorry, that's supposed to say of, the compound amounts of all the payments compounded to the end of the term. Here's an example of an ordinary annuity. Suppose $1,500 is deposited at the end of each year for the next 6 years into an account paying 8% compounded annually. How much will be in the account at the end of that period? So they're going to deposit the money in for 6 years, and it's going to be compounded in the interest only once a year, so 6 times. Here's what's going to happen. In the first period, at the end of the first period, I'm going to deposit $1,500 at the end of that first year. And then at the end of the second year, I'm going to deposit another $1,500. And at the end of the third year, I'm going to deposit $1,500. And at the end of the fourth year, $1,500. At the end of the fifth, $1,500. And at the end of the sixth, $1,500. So what I've actually put in total is 6 times $1,500. So the amount of money I have is $9,000. That's how much I put in over the course of 6 years. Or whoever has this. But then what happens at the end of that, and this is almost like the compound interest formula. At the end of that first year, they take my $1,500, they multiply it by 1.08 because it's an 8% interest rate. And they add that much interest to my original $1,500. And then at the end of the second period, they take that $1,500 and they multiply it by 1.08, 1 plus the interest rate, raised to the second power because this is the second compounding period. And in the third, $1,500 times 1.08 for 3 compounding periods and so forth. But then you add all of those together. Remember the one thing is that your last payment doesn't get any interest because you deposited at the end of the compounding period. So you're not getting any interest on your last payment. You do get interest on your first one, but not your last one. So here's what happened. Remember, I put in, how much was it? $9,000 total. Not even $9,000 at once, $9,000 periodically, collectively. My annuity formula says that I take my payment amount, I raise my rate to the 6th power, my 1 plus my interest rate, and then subtract 1. The reason you subtract 1 is because you didn't get any interest on one of those compoundings. And then your interest rate minus 1 is 1.08 minus 1, which is just going to be 0.08. And if you do the arithmetic, you should get $11,003.89. Okay? There's my numerator. And I can do 1.08 minus 1 in my head. I'm pretty sure you can too. So there's your amount. Now you could have done that all in one calculation. You just have to be careful to put your parentheses in the right place. Okay? And basically what we're doing when we have an annuity is it's the sum of a set of geometric terms. We're not going to talk a lot about sequences and series in this class, but it's using a geometric sequence. And that's where the formula actually comes from. So if you want to find the future value of an ordinary annuity, and they do not use A for the future value of an ordinary annuity, they use the word S because it's the sum of a bunch of different compoundings and deposits. S is the future value. R is how much you pay at the end of each period. I is the interest rate per period, and N is the number of periods. And this is the actual formula, but it can also be written as R times S sub N over T, or N times I. This is probably the one that's easier to calculate. The other one's just a shorthand notation. So let's work an example of that. First of all, we're going to do an ordinary annuity. Find the accumulated amount after 11 years if you deposit $250 every month in an account paying 3.3% interest, compounded monthly. So we're going to use the future value of the ordinary annuity. This is our formula. R is your payment amount, that's the $250. N is the 11 years, compounded every month, so times 12 months. And the interest rate is 3.3% or 0.033 divided by 12 for the 12 months. So there's your interest rate, I. And you plug into the formula, 250 times 1 plus the interest rate, raised to the power 132, because 11 times 12 is 132. Minus 1 over the interest rate per period. And it turns out that after 11 years, you'll have almost $40,000. So if you have a fairly good investment account and you can afford to put $250 a month in that account, you will have a nice amount of money at the end of 11 years. Questions? And in case anybody gets lost taking their notes or misses out on a few things, I am going to put the PowerPoint in D2L at the end of class today. It's just that I'll have to take it down and put it back up as I add the last section to it. So here's another example. Leslie Mitchell is an athlete that believes that her playing career will last 7 years. To prepare for her future, she deposits $24,000 at the end of each year for 7 years in an account that pays 6% compounded annually. How much will she have on deposit after 7 years? And then part B, if instead of investing $24,000 at the end of each year, what if she deposits $2,000 at the end of each month for 7 years? In the same account paying 6% compounded monthly, how much will she have in 7 years? Which one do you think she's going to have more in? If she compounds at the end, or if she deposits at the end of each year, or she deposits a lesser amount, although it's still the same annual contribution, but she compounds 2,000 of it, she deposits 2,000 of it at the end of every month. Which way is she going to make more money? What do you think?
The second way.
The second way. That's right, because you're compounding more often, and even though the payments are smaller, it's being calculated on every single payment. So her yearly payments are an ordinary annuity where R is $24,000 and the interest is compounded annually. M is only going to be 1. The number of times per year is 1. The number of periods is 7 years, once a year, so N is going to be 7. And the interest rate is 0.06 divided by 1, which remains 0.06. So we use the formula for the future value. And that's just notation. This is actually the way you plug into the formula. So it turns out that at the end of 7 years, she has $201,000, $201,452.10. 201,452 is, maybe that's enough for her to live on. She might need to get a regular job. So notice that she made 7 payments of $24,000, which is $168,000. The amount of interest that she earned was actually only $33,452.10. Most of that money was her own. But if you do Part B, the interest is going to be compounded monthly, and she's going to pay compounded monthly, which for most of us is easier to do. So that means that her number of compoundings is 84, even though her interest rate at each one of those compoundings is only 0.5%. So using the future value of the annuity with those changes, she has $208,147.85, and she got a lot more interest than she did the other way. Okay? So we're going to stop there, and we will pick up with your turn 2. If you want to look ahead, it's already on your notes, and you can see if you can go ahead and work it, and we'll be ready to start sinking funds.